Hey guys, welcome back to another video. And today we're going to be doing something real big this time. Let me make sure we're kind of on the right track here. Where are we? Today we're going to be doing something really big. We're going to be practicing for the unit exam tomorrow. You know, we have to go over every single one of these things right here. So, there's no time better than the present to get started, right? So first we're going to be starting with learning target 1. I can define heat and temperature. Okay, that's real easy. Alright, so to keep things simple and quick here. Okay, so I just lost my pencil. We'll find it in a minute. Essentially, what heat is remember from the calometry experiments we did, right? Anyways, what was I talking about? Oh yeah, heat. So there's a difference between heat and temperature, right? Heat and temperature are not the same thing. To put it very simply, heat is the transfer of energy from two things. So, heat is like that. Heat is going to be the transfer. Now, this may be complicated, right? What do you mean transfer? Well, remember our calometry experiments where we measured the heat and temperature, right? However, heat is going to be like maybe, as an example, what is this, joules per kilogram of whatever. That is heat, is the rate of transfer of the temperature from one thing to another. That is what heat is. It's the rate, it's the transfer. It's not the actual temperature itself, it's the transfer of it. Now, temperature, of course, is just how hot or cold something is. That's essentially what that is. Okay. So now that we've done that, we can go ahead and check off that. Okay, system and surroundings. I can define system and surroundings. That's pretty simple. System is just what we're looking at, what we're measuring. So the system, so let's say, we had an environment where there was this, barrier, and we had two circles. And we were transferring energy from this guy, and this guy was transferring energy from that guy. That's a closed system. So there's no way heat can come out or in. That's a system. And out here is the surroundings. That's what surrounds this. Now, an open system would be heat can come in or come out. Of course, almost all systems are open, or at least try not to be, because, it's impossible to have a completely closed system, but we try. Okay, so we can go ahead and check that off. Now, next one, I can define thermal equilibrium and give examples. Okay, easy. Thermal equilibrium is simple. Essentially, whenever you have one object, let's just call this one hot, and one object, let's call this one cold, and we take them and we touch them together, so now the hot object is touching the cold object. After some certain amount of time, these objects, after maybe, let's give it 10 minutes, they will reach a state of not hot or cold. They'll reach a state where both of their temperatures are equal. So now, if we were to take the reading, give it a second. Okay, so the temperature says it's 32 degrees Fahrenheit. That's how the temperature of these compared to this one, which may have been what, like 100, and this one, which may have been 0. That is what is the thermal equilibrium and an example of it. All right, so we can go ahead and check that off, right? I can define the law of conservation of energy and the law of conservation of mass. Well, that's simple. Two simple things. Law of conservation of energy. Energy cannot be created or destroyed. So no matter what, energy will never, ever be created or destroyed. It's always transferred. So let's say I were to burn a piece of wood, or a piece of paper, more simply. That piece of paper, even if it turned into ash or you can't even see it, that doesn't mean that piece of paper is gone. It's just transferred into like a new state of matter or a state of being. Now, what was it? The law of conservation of mass, same thing. It's kind of the same thing, except just like a little bit more complicated, right? You can't exactly lose mass or gain mass to something. It's always going to be, you can lose mass. Like, let's say we had like a boiling pot of water and we boiled it. Of course, we're going to lose some mass in the pot, but we're not going to lose mass that water doesn't just go away forever. It's just transferred into gas, steam, right? So we can go ahead and check that off, right? Now I can identify the parts of a system and the surrounding. Well, all that is, the parts of the system, it's just different parts, and then parts of the surrounding. Obviously, it just depends on what, you have. Like, parts of the system, like, let's just say this was a system. You can identify this and this as being parts of the system. However, the space out here is part of the surrounding, right? So you can go ahead and check that off. I can define entropy and give examples of how entropy is increasing or decreasing. Now then, entropy is just a wee bit more complicated, but it can be kind of boiled down if you really think about it. Entropy is really just entropy is just the simple, essentially, it is just the measure of the disorder or chaos in a system. So let's take this as water, right? This is water in its gaseous form. This is going to have a lot more entropy. So let's go ahead and, this isn't official, but let's just say entropy is E. This has a lot more entropy than a block of ice. So this is like an ice cube, right? Forgive me, ice cube. This is going to have a lot less entropy than this. Now, all we're doing here is we're comparing. We're not saying that this has a set amount of entropy. We're just saying that this has less entropy than that. It's very, very simple. Now that's, we just checked off that one. I can explain the similarities and differences between heat and temperature. Well, we already did that, really. Explain each of the 4 laws of thermodynamics. Now, this one's a bit more difficult. All right, this is a bit more complicated because I don't know if I'm going to remember all this. Because there's 4 laws. The 0th law. Are you serious? The 0 law, which is, we already explained it. Thermal equilibrium is the 0 law. The first one, matter cannot be created or destroyed. The second one is entropy. And the third one is the concept of absolute zero. Now, if we haven't explained absolute zero, the basic concept or idea of it, you might have to turn your phone for this one, but the basic idea is that at a temperature of absolute zero, all particles will come to a stop. That's basically it. Now, I don't have a thing for remembering this, but remember, just all you need to do is remember the 0 law, thermal equilibrium. The first law, matter cannot be created or destroyed. The second law is entropy, and the third law is absolute zero. You also have to remember it says in here for entropy, the entropy of a system always increases naturally, and, heat moves from hot to cold, as well as every process is less than 100% efficient. A process cannot be more than 100% efficient, because that breaks the law of thermodynamics, which basically is just like, you can't be 100% efficient. It's kind of like the perpetual motion machine, right? You can't have one. Now, we've done that. I can explain how a system transfers energy between the system and the surroundings. Well, I mean, if it comes in a contact, if like direct contact like that, if it can also radiate out heat because, it'll just put heat into the air. It's not that hard. Explain examples of each law in real world scenarios. Gotcha. All right. So that's going to be a bit more simple. Thermal equilibrium. We take a hot pan. We take a cool pan. We put them together. They'll eventually, be together. The first law, if you burn wood, the wood that's burnt isn't just going to evaporate. It's not going to, it might. The wood that you burn is not going to just go nowhere. It's going to turn into something else. Matter cannot be created or destroyed. The second law, which is entropy, that one, a real world example, Oh, that's a perfect example, actually. Turn your phone. You put liquid dye in a cup of water. It's going to spread out. Fourth example, absolute zero. In some cooling chamber somewhere, things are just going to stop moving. There's no kind of real world example. Things are just going to stop moving for that. Now, we've done that. Now the purple thing, I can explain how energy and entropy